Today we'll be learning a new rule to help us to differentiate complicated looking functions, such as this one over here, 3x minus x squared all to the power of 5. Now this is quite complicated because what you would usually need to do is expand it first, and it's to the power of 5, so it's going to be quite long, and then you would simplify it, then you would differentiate, and you might want to factorize it at the end to make it look quite simple. Well, luckily for us, there is actually a rule to help us complete this. What I'm going to do today is firstly try to explain the concept through an example. Then I will explain the theory, and then finally we will do examples to apply that theory. So first of all here, we can see that this function is in fact a composite function. It is a function within a larger function. So 3x minus x squared is the inside function, and then the outside function is this inside term all to the power of 5. Just to help with our explanation today, instead of f of x, I'm going to rewrite this as y. So for our inside function, instead of using this big term, what I'm going to do is I'm going to call that u. So I'm going to let u equal 3x minus x squared. Now, how does that help me in differentiating? Well, now I can rewrite this whole function as y is equal to u to the power of 5, which is quite nice because if I were to differentiate this, I will end up with dy by du 5u to the power of 4. Which is very useful for me because now I have been able to differentiate it. But the problem is I don't really care about u. I'm not looking for u. When I'm looking to differentiate, I'm looking to find dy by dx. So my next question is there any function that exists at the moment that is in terms of x that's going to help me find this? Well, yes, I have my u function. So u is equal to 3x minus x squared. So I can differentiate this. This will be du by dx, and differentiating that will equal 3 minus 2x. Again, whilst that's helped me reach my dx goal, I have something now that's in terms of dx, I have something that's in terms of dy, I don't have dy by dx. So is there something I can do to merge these two together? So if I try to use my fractions, I am looking for dy by dx. My dy is at the top, so I can use this function over here. And then I want my dx at the bottom, so I can use this function over here. So there's going to be some sort of relationship between these two functions. The problem is this du. Is there any way that I can get rid of it? Well, if I multiply these two functions, what I can do is cancel out the diagonal. So that's du and du can cancel out, which will result in dy by dx. And this here is the theory behind the chain rule. So what is this actually telling us? All it's simply telling us is that the overall derivative of a composite function is equal to the derivative of the outside function multiplied by the derivative of the inside function. What does that look like in terms of the example here? Well, if we've now learnt that this would be dy by dx is equal to the derivative of the outside multiplied by the derivative of the inside. Well, the derivative of the outside we've found already, that's 5u to the power of 4. The derivative of the inside we've also found. Since I have more than one term, ensure that you place it into brackets. And again, I've got this random term u that I don't really like. So what I'm going to do is I'm going to now substitute back the original function of 3x minus x squared. And I can just leave it like that. I don't need to factorize. I don't need to expand. This is an appropriate answer there. Now, this looks like a really long process, so what we're going to introduce a slightly easier way to be able to think about it. Rather than having to go through this whole process where we make u equal to something, differentiate that separately, differentiate the outside, and then multiply them together, you can sort of do it all in one step by remembering this idea. It is the derivative of the outside multiplied by the derivative of the inside. So if we were to practice that specifically with this rule here, all you need to do is treat this as though it's a single term when we're differentiating the outside. So just leave it as it is, don't touch it. So what I'm going to do is I am going to differentiate the outside. So that means I'm going to take the 5 out the front. This term stays as it is, don't touch it. Subtract 1 from the power, so that will be to the power of 4. And now what I'm going to do is multiply that by the inside, the derivative of the inside there. So that's times in. Derivative of the inside is just 3 minus 2x, and ensure you place that in brackets. Now what I can do is go ahead and simplify all of that. That will be 5, 3x minus x squared to the power of 4 times 3 minus 2x. And what you'll notice is that we've got the exact same answer. Without having to do all of this background work, we can go straight to it by remembering the rule. Multiply the derivative of the outside by the derivative of the inside. That there is the chain rule. So the chain rule is used to differentiate composite functions. We've been using this notation here, which helps us understand because the du's can cancel out. But another way to be able to think about it as well, if we have a function h of x, this is how we can write our composite function. So the inside we can call g of x, the outside is called f of x. The derivative is simply equal to the derivative of the inside multiplied by the derivative of the outside. And you can notice that when I'm multiplying it by the derivative of the outside, the inside term stays as it is. That's our u. So again, we said don't touch it, just leave it as it is. Notice previously, or in this notation, we've got the derivative of the outside multiplied by inside. It sounds like it's the opposite, but when you multiply something, it doesn't matter what order you do it in. So as long as the derivative of the outside and the inside have been multiplied together, it doesn't matter what order it is. That there is the chain rule. So now let's go ahead and apply that to a few examples. So in example 10, if we have our function f of x equal to 3x minus x squared all to the power of 5, which is exactly what we've just done. They want us to find f dash of x. We've already done that. Now we need to find f dash of 1 and f dash of negative 2. In case you didn't write that all down, let's go ahead and very quickly do that again. So we want the derivative of the outside. So that's taking the 5 out the front and subtracting 1 from the power. As we said, we're going to ignore the inside. It's just one term. You don't touch it. Multiply that by the derivative of the inside. So the inside is 3 minus 2x. And then we can go ahead and simplify that. And by simplifying it, really in this case, all we've done is gotten rid of that multiplication sign. Now we've finished this f dash of x. Now we're up to our first step where we're going to find f dash of 1. So all I'm really substituting x is equal to 1 into my function. So wherever I see an x, I'm just going to put in 1. And I'm going to be simplifying that. So 3 times 1 is 3, and then that's minus 1 squared, which is 1. So that will equal 2 to the power of 4. And this is 3 minus 2, which is just 1. 2 to the power of 4 is 16, and 16 times 5 will be 80. So now that part is now done. Finally, we're going to answer the derivative when this time x is equal to negative 2. So same thing. I'm just going to rewrite my derivative function. Wherever I see an x, I'm going to insert a negative 2. Run out of space there. So 3 times negative 2 is negative 6. Negative 2 squared is positive 4, and then I've got a negative there. 2 times 2 is 4, so that will be 3. And this, of course, don't forget your negative 4 there. Negative 6 minus 4 is negative 10. Negative 10 to the power of 4, this is going to be quite a large number. That will be 10,000. So to the power of 4 means there's going to be 4 zeros, and because it's a positive, an even power, that means our positive will disappear. So 5 times 7 is 35, and 35 times 10,000 will be 350,000. Another one now. So if f of x is equal to this function here, again find f dash of 2 and f dash of negative 1. But before I could do either of these, I have to find the derivative function. So what you can notice again is that this is my inside function. We can call that u, but I won't be writing all of it out as let u equal and then find the derivative. I'm just sort of going to do it in my head. So in order to find the derivative, we need to remember the rule. It's the derivative of the outside multiplied by the derivative of the inside. The derivative of the outside involves taking the -3 out the front. Again, we don't touch the inside, just leave it as it is, and subtracting 1 from the power, so that will be -4. And then I'm going to multiply it by the derivative of the inside. So the derivative of the inside, which we've called u, will just simply be 2x minus 1. That takes us straight to our answer. And if you'd like, and to make it a little bit easier to work out our values, we can take our negative power to the bottom. So I will leave 2x minus 1 at the top, and x squared minus x will go to the bottom for the power of +4 at the bottom. All right, let's go ahead and start substituting in. So f dash of 2, so we're going to substitute a 2 wherever I see an x. Two times 2 is 4, minus 1 is 3. 2 squared is 4, minus 2 is 2. And 3 times 3 is 9, there's a negative, and 2 to the power of 4 is 16. So I'm going to get -9 on 16. Now I'm going to complete it for f dash of negative. So wherever I see an x, I'm going to be substituting in -1. Two times -1 is -2, minus another 1 will be -3. -1 squared is +1. This should have a bracket around it, sorry. +1, negative and a negative make a positive, so that's just 1 plus 1. -3 times -3 is 9 on 16. Next example. Now, again, this is a composite function. We've got our inside function u here compared to our outside function, which is the square root of u. The other thing is, though, it's at the bottom. So what I can do to simplify it is, firstly, I can put it to a power of a half. And secondly, I can take it to the top. By making the power a negative. Now I can go ahead and differentiate this a little bit easier. So my inside function here is u. Remembering our chain rule, the derivative of the outside multiplied by the derivative of the inside. Take the -1/2 out the front. 2 times -1/2 is -1. Leave the inside as it is. -1 minus -1/2 minus 1 is -3 on 2. And I will be multiplying that by the inside, the derivative of the inside. So the inside is 2x minus 4, as we've already established, that's our u. The derivative of that inside is just 2. So in order for me to simplify it, I'm just going to leave our -2 up the top, and I'm going to take 2x minus 4 to the bottom. This is to the power of 3 on 2, so the on 2 makes it a square root, and the 3 means it's cubed. Of course, you can leave it as to the power of 3 on 2, but this just looks a little bit neater. Now all I need to do is find out what the value is when x is -1. So wherever I see an x, I'm going to substitute in -1. Two times -1 is -2 minus another 4. -2 minus 4 is -6, which can be rewritten as the square root of -6 cubed. Now the issue is you can't actually take the square root of a negative number, and so this would leave this function to be undefined at -1. For our final example, it's going to be exactly the same. As you can see, we have a function on the inside, x squared minus 3x plus 4. That is our u. and our outside is this square root. Now you can, just for yourself if you'd like, write this as the outside, that's root u, or u to the power of a half. So step 1, find f dash of x. We know this is the gradient of the outside multiplied by the gradient of the inside. Taking the half out the front, and then leaving the inside term as it is, x squared minus 3x plus 4, and subtracting 1 from the power, a half minus 1 is negative a half. Then I'm going to multiply all of that by the gradient of the inside. So that is going to be 2x minus 3. But it looks quite neat. 2x minus 3 on to square root x squared minus 3x plus 4. Now for part B, all I have to do is substitute in x is equal to 2 into my derivative function. Two squared is 4. 3 times 2 is 6 plus 4. The top 4 minus 3 is just 1. And at the bottom, 4 plus 4 is 8, minus 6 is 2. And so the answer here is 1 on 2 root 2. I probably don't need this long square root. What we can do is we can rationalize the denominator by multiplying both the top and bottom by root 2. So that will equal root 2 on 4.